Okay, we're now recording. We're on the second half of the 7/2 notes, and we're talking about simple harmonic motion. Remember, it's motion that regularly repeats, kind of like a spring going back and forth. And that was actually the discussion topic we had, and we'll look through your responses. So make sure you get a response in by tomorrow morning before class starts. This motion that regularly repeats. Frequency is actually independent of amplitude. So here are some different formulas that we can look at. So remember, T is going to be hold on a sec here. Okay. Yeah. So T is going to be I believe that's dealing with period, if I'm not mistaken. Hold on a second here. Yeah. So T is going to deal with period. M is going to stand for mass. F is going to stand for frequency. And K is going to be the spring constant. Remember, period is always going to be measured in seconds. Mass is in kilograms. Frequency is seconds to -1 power, or we call it hertz, Hz. And spring constant is going to be a Newton per meter. So if we kind of just examine this in a little more detail, remember, M is mass, so that's kilograms. K is going to be a Newton per meter, so it's a Newton per meter. Now remember what a Newton is. 1 Newton is a kilogram times meters per second. So if I flip this over, kilograms times meters over a Newton, which is a kilogram times meters per second squared, those cancel. And if you flip that over, meters times second squared over meters, those cancel. And remember, you're square rooting the whole thing, right? The whole thing's being square rooted. So what's square of s second squared? Just seconds. And there you go. So that's why that formula works the way it does. So it always helps to know your units in some of the algebra. And then frequency, of course, is that flipped over. So these, of course, are reciprocals of each other. So if you know the mass of your spring and the spring constant, which is basically indicative of the firmness of the spring, you should be able to figure out the period of like how long it takes to do one cycle. And the frequency is how many cycles you get in one second. So you actually could determine that from these formulas here. Think of a point on a string, some distance x from the origin. So if we think of it as having some distance, and the distance we call x from the origin, and we want to know the vertical displacement of the particle at any given time, then we actually can determine that with some formulas. And one of those formulas we can use is actually just right here.
I think I need to, if you can move your car. Oh, yeah. Great. And we'll see.
Where A is going to stand for the amplitude.
Yes.
And again, capital T was the period. And t is the time that's passed. So how much time has passed? We should be able to figure out the amplitude of the wave as a result. And the wave repeats, it tends to look like a sine or cosine graph.
Okay, I'm not.
Again, for those who haven't had trig, sine cosine graphs look like this.
Just gonna, come here.
They're just waves, that's all. And you'll learn about it when you guys take pre-cal in the fall if you haven't done pre-cal yet. So we're now going to do the work right below here. So we'll do this example on the next page. Then I'm going to do 5, 6, 7 for you guys, and then have you guys do some work in groups. So anyway, the wave has an amplitude of 1.5 centimeters. Now remember, you always want the amplitude in meters, because everything we're doing here is in meters. So we need to convert that. And we're using this formula, y equals a times cosine 2 pi little t over capital T. And again, the 1.5 centimeters, we'll have to convert that to 0.015 meters. Because remember, 100 centimeters equals 1 meter. So the decimal point here has to actually move 2 places to the left. That, of course, our frequency is right here. And this is our velocity is 20 meters per second. Actually, I'm not sure if we will even need to know that. But here just has to write the equation of the wave position of the wave. And actually, you should be actually told to write the equation as a function of time, which we call little t. So in this case, it will just be y equals 0.015 times the cosine of 2 pi little t. And you're going to divide that by your period. Now, if our frequency is 100 hertz, remember frequency is 1 over the period, or the period is 1 over the frequency. So if I do 1 over 100 hertz, that's 0.01 seconds. So I'm going to divide that by 0.01 down here, or I would just get this. Let me tuck it in right below here. Times cosine of 200 pi t. And so that would be an equation that you could write to represent this wave. So, okay, that kind of covers the notes here for 7.2. So again, the main formulas we talked about were these two right here, which again, you don't have to memorize anything, everything's open note, so don't worry about that. This is an equation used to write, to represent the wave, to kind of represent its amplitude. So this equation would actually graph this, just so you know. That's what we're noticing here. There are some formulas for velocity that could be expressed a little differently, like velocity could be force over mass divided by length. Also, potential energy, that's only clear the screen. Potential energy of a spring is right here, and force is also right there. So a lot of different formulas are going on. So let's actually look at some of these problems right now. So again, I'll do 5, 6, 7. I probably need maybe about 10 minutes, maybe more or less. And then I'm going to give you guys till 11 o'clock. So probably around 10:40-ish. I'll let you guys try 8 through 15. These should go by pretty quickly. And we'll check in again. Maybe I might give you guys a little more time to do these problems, because I want to make sure you guys are spending a good amount of time on that. So let's start with number 5, and I'll have kind of people in the room help me out. So number 5 has 3 parts. Number 6 has 2 parts. Number 7 has 2 parts. So this is perfect. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9. Looks like everyone is here. Okay, so let's get started. So let's look at number 5. The first person I see Justin, first on my list. So you're gonna help me out with part A. So let's actually read through this first. Fish are hung on a spring scale to determine their mass. Most fishermen feel no obligation to truthfully report the mass. I don't fish, but I know that's kind of a sense of pride if you catch a fish that's really heavy. Was a force constant of the spring in such a scale? The spring stretches 8 centimeters for a 10 kilogram load. Now remember the formula for that is this. So we call it negative kx. So so Justin, help me out here. So what are some things I could plug into this equation right now for number 5A?
You could plug 10 kilograms and 8 centimeter stretch.
Okay. So now, if we think about you hanging a fish, again, I don't fish, but I have seen enough photos on Facebook when people brag about it. How are they actually measuring the weight of the fish? Like, what do they do? So you catch a fish.
They hook. I'm pretty sure they hook their
They
mouth
hook it,
up
right.
and then
And what's
hang it.
weighing that fish down?
The fish's weight.
Yes, which is gravity. So the force is going to be mg actually.
Gotcha.
And so that mass, now we know 10 kilograms, but what am I going to plug in for g?
9.8.
Yeah, and we'll make it negative actually, because it is pointing downwards, right? And you got negative k, and then obviously the scale is lowered a little bit, because right now you have the little hook, and then you put the fish on, and it goes down a little bit, and of course it goes up by 8 centimeters. But remember, gravity is in meters per second squared, the acceleration due to gravity. So how will they have to change 8 centimeters?
To meters.
And what will that be?
0.08.
Thank you so much. Okay, so thank you, Justin. That's awesome. The negatives will cancel, obviously. So I get negative 98 equals negative 0.08 K. And if I were to work it out, so there's a spring in that scale, obviously. I mean, that's because then when you take the fish off, it recoils and goes back up, right? Divide by negative 0.08. So the spring constant's 1225. And it's a Newton per meter. So for every meter, there's 1225, or it takes 1225 newtons, I suppose, to get to go down 1 meter, if you want to think of it that way. And that's why it's going to be a constant, right? Because force over x equals k. So it takes 1225 newtons to bring it down 1 meter. In our case, because the fish weighed 10 kilograms, it was 98 newtons, took it down 0.08 meters. So if I did, 98 divided by 0.08, I got 1225. So it's just a direct relationship. That's all that's happening. The more you stretch the spring, the more force you got. Makes sense, right? Or more force you have, the more it stretches. So it should be pretty straightforward. They did it in scientific notation to kind of get fancy on us, but who cares? 1225, I'm totally cool with that. Okay, so again, thank you, Justin, for that. So now we know what K is. We're going to use that. So Steve, I see you next. So for part B, now what mass of fish will cause a spring to stretch 5.5 centimeters? So again, we're going to use the same formula. F equals negative kx. So what can I substitute into my equation now, Steve, for part B?
K.
Which is negative 1225, good.
Yeah.
So negative 1225. And then what can I plug in for x?
Yes.
And what's that going to be for part B?
Is that negative 9.8?
No, x. X is distance.
Oh, sorry. Is that, 0.08?
But we're doing part B, not part A anymore.
Oh,
Number 5.
Sorry. Oh, 5.5.
but we need it in meters.
Oh, right.
Remember, where should you move the decimal point?
Oh, over, sorry, 0.055.
Thank you. Perfect. Thanks so much. 0.055. And now the force, we want the mass, right? So remember, it's going to be mg again, and you're going to use negative 9.8.
Yeah, sorry.
Right. That's where negative 9.8 is going to go. It's going to go for the exertion due to gravity. So remember, the force that's happening because you're weighing it down, so you have to kind of visualize this. So now we can solve for the mass of the fish. And obviously, it's not going to be as heavy as it was in part A because it didn't go as much. So negative 1225 times negative times 0.055 divided by negative 9.8, you get 6.875 kilograms. So not as big of a catch as part A. Okay, so that's part B. And then part C, how far apart are the half kilogram marks on the scale? Okay, that's a fun one. Yeah, so, and I guess the way that works is that I believe it's kind of, going to show itself as a vertical scale. So like, as you weigh it down, like it shows like, okay, it's, here's how much weight or mass you have. So part C is going to be a little bit tricky, but I'll kind of give you a strategy. So Jonathan, I see you next, so you'll help me out here. So let me clear this. So for part C, they're asking how far apart the half kilogram marks. So what we're going to do is we're going to make up two masses, 1 kilogram and 1.5 kilograms. So we're going to calculate two different distances. So again, Jonathan, how do you help me out? So F equals negative kx. And let's focus on M1 right now. So we'll call this force 1.
All right.
And X1. So we'll do that right here. So again, because this is weight due to gravity, I'm going to do mg. So m1g. So what am I plugging in for m1 again?
M1, that would be the mass, right?
Right, and I remember I made it up. What did I make up for m1? It's on my screen. Can you see my screen?
Yeah, I can see your screen.
I'm underlining it.
Excuse me?
I'm underlining it.
Oh, 1.
Yeah, exactly. And G, of course, negative 9.8. And what was our K again? That we get from part A? And Jonathan, you're muted.
Oh, it's 1225.
Right. So you want to solve for x1, which is going to be pretty small. If I do that, I should get this. Negative 9.8 divided by negative 1225, I get 0.008. Remember, this is in meters, mind you. Okay, so Jonathan, I'm going to have you do this calculation again. But now, you're going to replace, you're going to do m2g times negative k times x2. So remember, m2 is 1.5 because I made that up because remember, you're doing half kilogram mark. So you're being hypothetical. Like, okay, what if a fish weighed 1 kilogram? What if fish weighed 1.5 kilograms? How does this change? So go ahead and, if you have a calculator or you can use a cell phone, whatever makes sense for you. Tell me what you get for x2.
X2, okay, give me one moment.
Yeah, take your time.
As x squared or x?
No, this is x2. It's one variable.
X. Okay. 0.012.
So thank you so much. And then the difference between this and this, of course, is 0.004 meters, or 4 millimeters. So it's very, very small, like each half kilogram mark on the scale. And actually, when people design or manufacture these scales, they have to first know the spring constant, and then realize, okay, then you calibrate it, and then they kind of figure, okay, when we actually make the scale, we have to make sure we're separated by 4 millimeters for each half kilogram mark. Actually, let's take a look right now. Scale used to weigh fish. Okay, well, obviously this is a little more fancy. But that's for cannabis, so we didn't talk about that. So let's close that one down. It's legal, but yeah. Okay, I don't know why that showed up. I said fish, not cannabis. Right. This one looks like a good one. Oh, duh. There we go. Yeah, so this is kind of cool. I wish I could zoom in. Yeah, so you can kind of see, they do in pounds, obviously, because in this country we do pounds. But you can see how they kind of separate, and it's kind of calibrated very nice, and then there's a little like hook at the end. And this can be used like not just measure fish, but maybe like produce or other types of stuff. If you're working in a restaurant, that's kind of important because you kind of want to make sure you're pretty consistent with the food you serve and your portions. Let's see here. Let me close that one down. I mean, there's a fisherman there, obviously, but he's using a digital one. Images. Yeah, here's another one, but anyway. So hopefully throw the fish back into. Some people don't like to kill or eat it, but all right. So that's number 5. So thank you guys for helping me out there. Okay, now let's look at number 6. Actually, 6 is very similar, so maybe I don't want to do 6. I want to give you guys an opportunity to do that. So let's look at 7. No, 7 is also similar too. Let's do 8, because 8's a little bit different. And I think that's kind of a good thing to do. I'm just looking at the questions here. Press spring. Okay. Actually, no, let's do 7. 6, I think you guys should be. Yeah, I think you guys should be fine for 6. Let's look at 7. So for 7, one type of BB gun uses spring-driven plunger to blow the BB from its barrel. Okay. Calculate the force constant of its plunger spring. If you must compress the 0.15 meters to drive a 0.05 kilogram plunger to a top speed of 20 meters per second, what force must we exert to compress the spring? Okay. Now in this case, so we have a gun, right? I'm not really good at drawing guns, and you have a little thing here that gets fired off. So and there's a spring inside that kind of coils it. So initially, their velocity is 0 because it's at rest. And you want to get to a final velocity of 20 meters per second. So initially it's there, finally it's there. And you're asked to calculate, excuse me, and you must compress it 0.15 meters to drive it to a top speed. Okay. So So by the time it leaves at 20 meters per second. So you remember some of our kinematic formulas, right? So remember we have v squared equals v0 squared plus 2a x minus x0. So your final velocity is 20, your initial velocity is 0. And if you solve for acceleration, I think the distance, this is 0.15. So if you solve for acceleration, remember 20 squared is 20 times 20, which is 400, divide by 2 and divide by 0.15. So acceleration is pretty darn fast. Which would make sense if you're shooting a gun, right? That you expect that to happen. And remember, if you're calculating the force constant, so force equals negative kx. Force is going to be mass times acceleration. So you have the mass, and you try and figure out what k is. And again, the distance is 0.15. And our mass is 0.05. Again, our acceleration was 1333.33. And I suppose the whole negative part, you're actually kind of coiling it back. So I guess we can make that. You can always give k as a positive value regardless. And if you solve for it, 0.05 divided by 0.15 times 1333. Interesting, I'm off by a factor of 2, and I wonder why I'm off. So let me think about this one here. Kx. Not divided by 2? Let me think here. 20 squared is 400. Yeah, I'm not 100% sure. I'm off exactly by a factor of 2. If anyone can identify what I may have done wrong. Press at 0.15 meters. Huh. I want to double that distance. So I'm not 100% sure what I may have been doing wrong, but I know this is the method that you want to go through. Yeah, very, very interesting, because obviously you have your mass and you have the acceleration. And maybe they made a mistake, I don't know. But once you have that, then it's pretty easy to calculate part B. The force must be exerted to compress the spring. You just take your force constant times. But yeah, something seems a little bit off here to me. Yeah, don't know what's happened with that one. Let's just try one more. Have you guys tried these problems? Let's take a look at, or someone knows what I may have done wrong, Brandon?
Well, I'm not sure, but I think we could try like the potential energy of the I guess.
Yeah. The only thing is that let's let me think about that one.
The max kinetic energy could be the 1/2 mv squared.
Actually, you might have a good point. Actually, let's take a look at what Jonathan's saying. But I wonder why the way it didn't work. Let's conserve energy. Okay, so let's relook at number 7. So yes, initially you have 100% potential energy, right? So your P initial plus your KE initial equals your PE final. Now, initially you have all potential energy. That's going to be 1/2 kx squared plus 0, and that's going to equal your final potential energy is 0 because now it's in full motion, plus 1/2 mv squared. Yeah, I think you're on the right track. The 1/2s are going to cancel from each side, and you're solving for k, and again it coils back 0.15 meters. The mass is 0.05, and the velocity is 20 squared. That's what happens here. 0.05 divided by 0.15, divided by 0.15 again, times 400. Interesting. Okay, thank you. That actually did the trick. So conserve energy. Then you can get the force. Negative 888.9 times 0.15, right? And that will get us the answer. Times up by 0.15, you do get 133 newtons. Yeah, I still wonder why the other way didn't work though, because that should still, because they're all kind of connected, these equations, so I'll have to think about that one. But conserving energy, that obviously bailed us out. Let's take a look at maybe number 8. That's another form we can use. 9 is similar to 8. So let's take a look at number 8, and then I'll turn you guys loose to doing some problems here. For number 8, the mass of a string is that. It stretches at the tension 108 newtons, blah, 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 has that kind of frequency. So the formula we're going to use here is this. Velocity will be the square root of your force divided by your mass over length of the string, and that's what we want. We want the length of the string, which is called L. Well, velocity we also know is a frequency times lambda. So I could probably replace. Well, let's solve for the velocity first. The frequency is 260 hertz. Lambda is 60.6 meters. That's easy. Remember, you have to convert the units if it's not meters. So 156 hertz. Okay. Sorry, it's just 156. Let's say meters per second. Meters per second. My bad. So you have 156 right here. The force is 180 newtons because the tension. The mass is 5 times 10 negative 3 kilograms, and divide the whole thing by the length. So you have to be very, very careful with your algebra here. You got to flip that second fraction, which I put in parentheses. 156 equals the square root of L times 180 over 5 times 10 to negative 3. Square both sides. And you get L times 180 over, and multiply it by 5e negative 3, divided by 180, and I get 0.676 for L. So that gets us the length of the string. So that's number 8. So we already did 5, 7, 8. Now I want you guys to do number 6. and numbers 9 through 15. So that's 8 questions altogether. I think giving you guys about 22 minutes, so around 11:20 we'll come back. We'll go over any questions you guys have, and then we'll have our lunch break around 11:30. So hopefully that kind of makes sense what I want you guys to do. And I'll come by and check and make sure you guys are, excuse me, that you guys are doing okay. But all the forms you need should be right here on the, well, it doesn't show up, but you know what I mean, the 7-2 notes. So most of the equations you need should be right there. And so we'll work through those problems, and then we'll talk about it in about 20 minutes from now. So I'm gonna go ahead and clear all this. And let me stop recording.